And then once that's started, okay, excellent. Now I'll share my screen. So, right now I'm sharing my code screen. It should show my PyCharm window. If you guys can't see it, just let me know. Um, but yeah, so the first thing I'll do is I'll go ahead and go over just a very simple way to put layouts in IPKIS. And then I'll go over a more complex way. I'll talk about circuit simulations inside of IPKIS. And then I'll try to demonstrate a link to Lumerical for component simulation. So I'll kind of go over like the whole workflow with IPKIS. But yeah, and if at any time you have any questions, just feel free to interrupt me or like, use one of like the I guess what not it's not Zoom. Microsoft Teams has like the raise your hand feature. So just like if you have any questions, just either interrupt me or use that or type it in the chat. Um, but yeah, let's go ahead and get started. So first thing we do, of course, in Python is we import the things we want to use. So in our case, in line 24, we're importing our PDK. SciFab is a PDK that comes bundled with IPKIS. It's like a training PDK, so you can't really like tape out using SciFab, but you can get a good idea of how layout and design works with IPKIS. Then you import IPKIS, and then this kind of instantiates your code, and you're able to start putting layouts and designing components from there. One thing I want to mention as well is IPKIS has like a ton of like Foundry PDKs. So if you want to tape out at a specific Foundry, we probably have a PDK with them. And I know you guys do like internal fab as well. So if you wanted to make a PDK for your internal fab, we can certainly help with the process of putting that together. Um, but anyway, so first thing we're doing here is we instantiate our splitter tree class. So a class in Python is essentially just a blueprint. So we're saying that we want to make a blueprint for generating a splitter tree. And then we inherit i3.circuit. i3.circuit is a class inside of IPKIS that defines how circuits work. So we're telling IPKIS that everything inside of our splitter tree class is a circuit, that this all behaves like a circuit. Um, so the simplest way to make a layout is you define your instances or ints, and then you define your specifications or specs. So essentially here, what we're doing is we define our MMI as a 1x2 MMI optimized at 1550, and then we make three separate instances of that MMI. They're all that same MMI, but they're different instances of that MMI. Then once you define your instances, then we define the specs. So this is now where we tell IPKIS where the MMIs go and how the MMIs are connected. So as you can see between line 51 and 53, we have three place commands. We place our MMI 0 at the origin, MMI 1 at 100 minus 25, and then MMI 2 at 125. Then in line 57 here, we're using connect bend. Connect bend is a connector that comes bundled with IPKIS, like it's a connection like function. So we're passing in a list of connections we want to make. So here we're saying we want to connect the output 1 port of MMI 0 to the input 1 port of MMI 1. And then we're doing the same here, out 2 of MMI 0 to in 1 of MMI 2. And then in this last code block here, this I call the code execution block. So basically, once you finish writing your script, you put this sort of if statement at the beginning, and then put all the code that you actually want to run inside here. And then when you run this file, the only thing that will run is the code in this block. So here we have a variable called splitter tree. We're calling our splitter tree class that we just wrote. And then splitter tree layout, we're accessing the layout of that class. And then we're using a visualize command to visualize our layout. And then we use write GDS2 to write our layout to a GDS file. So when I run this guy, it'll go ahead and generate a layout. Here we go. So this is our layout right here, right? We have our three MMIs and we made connections with them using S-bend connectors. ConnectBend is an S-bend connector. Yeah. And then, a more advanced example would be something like this. Actually, before I continue, are there any questions? All right. If no questions, I'm just going to go ahead and move on to the next file. Um, so in file 4, here we instantiate some parameters. So this is just an upgrade from the first file. So of course, we have our import statements, we have our class that we instantiated, and then here now we set up some variables that define our splitter tree. So we know that our splitter tree needs a splitter. We know that our splitter tree needs grading couplers. And then we also know that we need to be able to change the spacing between our splitters. So we have our X and our Y spacing. So we define these variables and then we restrict them with these property restrictions. So I3.childCell property in line 24, this just means that the only thing that a splitter can be is a P cell. It can't be a positive number, it can't be a string, it can't be a Boolean, it can only be a P cell. Same in line 26, I3.positive number property. This means that spacing x can only be a positive number. It can't be a negative number. It can't be a Boolean, can't be a string, so on and so forth. So this just kind of helps to reduce errors in your layout. Maybe you accidentally pass a string into a splitter, and instead of the layout just completely crashing and you having to figure out what's going on, IPKIS can then tell you, hey, you passed a string into this, there's a property restriction error. Um, go ahead and fix that. And then, so earlier I talked about default ints and default specs. These are default functions that IPKIS looks for in the background. But for things like, the splitter and the grading coupler, where we don't have a default value specified yet, we can use the default function to specify the default values for these things. So in our case here, our default splitter, we are making a 1x2 MMI optimized at 1550. And then the default grading coupler, we are having that to be a 1550 grading coupler for TE mode. And then same thing here, we have our instances, we define all of our splitters, and then we define our grading coupler. But now this is where, the power of Python really comes in is, for all of our output grading couplers, instead of manually typing them in and hard coding them in there, we can use a for loop and just automatically generate these guys. So here we have a string, a dynamic string, where we're changing the grading number in our string, and the grading number is gonna range from 0 to 4 or 1 to 4. Technically 0 to 3 in Python because the Python index is at 0, but yes. It's going to generate 4 different output grading couplers, and then we're referencing our grading coupler here. For default specs, we place our MMI, our first MMI at the origin. The only difference between the first file and this one is that we are now placing it, we're now accessing the input 1 port of MMI 0. So what this is saying is place MMI 0 at the origin, but use this input port as the point of reference. So if you were to look at the layout, the center of MMI 0 would not be at the origin, but rather the port would be at the origin. So the MMI would be placed at the origin relative to its input port. And I'll show you what that looks like with a layout visualization. Then in line 58 and 59, we're doing the same thing, except now we have these spacing variables that we defined earlier, and we're using this relative to command or like variable. We're saying we want to place MMI 1 relative to MMI 0, use the input 1 port as the point of reference, and then we want it to be spaced at this X and Y spacing value that we defined. I3.join literally just takes two components, takes their ports and just joins them right next to each other. And then connect bend, again, we talked about this earlier, makes the S-bend connectors. In line 68 here, this is just some math to calculate the vertical offset for our gratings. Again, power of Python, we're using a for loop, and now we're appending to our specs list. We're placing all of our output grading couplers, and we're changing the Y position of it. The angle equals 180, that just rotates the grading coupler. And then we have our Manhattan connector. So this makes Manhattan routes. And again, here we have all of our connections that we want to make. This default exposed ports function basically takes the ports of your circuit, and you can then expose certain ports to be connectable when you take the circuit and export it into another circuit. So let's say you have this splitter tree that you made. You want to put it into a larger layout, put it into a larger circuit, and then you want to connect to it inside of that circuit. Um, you don't want to be able to connect to like the ports that are kind of like inside of the splitter tree. You want to connect to the input of the splitter tree and then the outputs of the splitter tree. So here what we're saying is we're redefining the ports, right? We're saying that the vertical in of our grading coupler in, we're going to rename that to be in. And then the output grading coupler 0, its vertical in port, we want to name that to out 0, and so on and so forth. And then in this code execution block, we're actually going to be generating two different layouts. So the first one, we're going to change the spacing to 50 and 100. And then in the second one, we're going to replace our splitter with a Y branch. And then we're going to change the spacing to be 30 and 30 and just make the layout a little tighter. So I'm going to go ahead and generate the first one, and then I'll kind of go over go over the code and this again. So in our so the first thing is our placement, right? We place MMI 0 at the origin with the input 1 port as the point of reference. If we take a look at our origin here, you can see the input port of our MMIs at the origin. Secondly, our join command, we're joining our input grading coupler to our MMI input. This is what the join looks like. And then what else do we have here? So we have our different connectors here, right? We have our, excuse me, we have our S-bend connectors at the beginning, at the first level, and then we have our Manhattan connectors at the second level. And then when I close this layout, it's going to go ahead and generate the second one. And so when we generate the second layout here, now you can see we've replaced our splitters with, we've replaced our MMIs with Y splitters. And we still have everything else the same, and our layout is also a little tighter. So, you know, the advantage of having scripted class-based layout is that you basically can have as many variations of the splitter tree as you want. So if you wanted to run a parametric study on like the spacing of your splitters for whatever reason, you can totally you know, change the spacing and generate a bunch of different splitter trees and test them out. If you wanted to, and you know, instead of having to instantiate 100 different classes, you can use a for loop and just iterate through all the spacings, generate all of them, place them into a layout. So there's a lot of power behind being able to script stuff in layout. Any questions regarding this so far? All right. Now I'm just going to go over some circuit simulations. So IPKIS has a circuit simulation model called Caffe. And the way that this works is that every component in IPKIS has a circuit model associated with it. And so actually, take a look at the MMI real quick. So to make a component or a P cell, it's pretty similar to making a circuit, right? You have your class, you have your MMI, except you inherit a P cell instead of a circuit. Then we have all of our properties for our MMI. So we know that the MMI has a width, has a length, has a taper width, taper length, waveguide spacing, cladding width, and then we have the MMI also has a trace template. Trace template essentially is the cross section of a waveguide. So this so if, instead of having to route, the core of your waveguide and then route the cladding of your waveguide, you just route the waveguide and it contains the core and the cladding already in it. This validate properties function is, it's not necessary, it's optional, but this just makes sure that you're not making a super weird MMI. And then the difference between a P cell and a circuit class is that you have to instantiate a layout class in a P cell. Not every P cell needs a layout, so that's why this is kind of there. So here we're just redefining all of our parameters so that we don't have to type self.traceTemplate or self.taperWidth in our uh, component generation. The generate elements function, you're just making elements here. So i3.rectangle, i3.wedge, these are shapes that are available in IPKIS, and we're just passing in these parameters to make these shapes. The arguments for this is available in the IPKIS documentation. And also you can reference this code and see what's needed for these shapes. But here we have our silicon core for the MMI. We have our 3 wedges for the input and output tapers, and then we have our cladding rectangle. Generate ports. This function right here makes the ports for our MMI. So here we we're making 3 optical ports, in, out 1, and out 2. We assign the position for these ports, the angle for the ports, and then the trace template. So when we assign a trace template to the port, basically when we connect between this MMI and another component, IPKIS already knows how to make that connection, right? It knows how to route it, but then it also knows what the material stack should be for that waveguide because we've defined the trace template. So circuit model, this is what I wanted to talk about. So the circuit model is a class that you can assign to your P cell. And basically this stores the behavior of your component. So this class right here is kind of like it's not, this class right here is a blueprint, right, for how a model should be implemented. But if we go into our locked P cell here, right, see here we're inheriting our 1x2 MMI. And so we don't have to redefine the code. We don't have to redefine anything. We just pass in the values that we want. So our width is 4. Our length is this value times 2 inside of i3.snap value. Our taper length is 5. Snap value basically just snaps your value to the grid size. But here in our circuit model class, we inherit our circuit model from MMI 1x2. We tell it that where to find the center wavelength from our data file, where to find the transmission, where to find the reflection. Yeah, so essentially, your circuit model is derived from like S parameters that you get from your not circuit simulation, sorry, from your component simulation. So when you like simulate a component in IPKIS, sorry, not IPKIS, in Lumerical, right? Like you can get the S matrix, you can get the behavior of that component out, and then you can tie that to a P cell in IPKIS and run circuit simulations in IPKIS. So in this splitter tree simulation file, actually, before I continue, any questions? I know I covered like a lot in that file. All right, if no questions, then I'll go ahead and move on to this splitter tree simulation. So one thing to note is that in here, we're not defining the behavior for anything, right? Even in our circuit, we don't define the behavior of the circuit because everything is derived from the component. Um, so in here, what we're doing is we import our PDK, import IPKIS, import PyLab, PLT for plotting, import NumPy for some math, and then we have a folder called circuits to simulate, and then we import the splitter tree from that folder. That's pretty much it. In this block of code, we're instantiating our splitter tree, instantiating the layout, and then we're going to visualize it just to make sure that we're simulating the correct circuit. Then in this block right here, we're going to call the circuit model of our circuit. So remember, circuit is a splitter tree class. We're going to call the circuit model of that circuit. And then we're going to generate a linearly spaced array of wavelengths starting at 1.5 to 1.6 with 501 points in between. Then we run the get S matrix function on our circuit model. And then we pass in the wavelengths that we want to simulate over. And then this is all just like code to plot our data. And then in this code execution block here, we're just visualizing the transmission and the reflection. So when I run this guy, first thing it's going to do is it's going to visualize our circuit. So this is a circuit we want to simulate. And then it's going to visualize the, excuse me, the transmission and the reflection. So this right here is our transmission. So this comes from all of these guys right here. And then we have our transmission from the input to all of our outputs. And then we have our reflection for the splitter tree. So simulating a circuit is in IPKIS is pretty straightforward. It's like you're not redefining the behavior of the circuit or anything like that. IPKIS knows how the components are connected. It knows the behavior of the components, and you specify the wavelengths you want to simulate over, and then IPKIS then the simulation engine in IPKIS knows how to work with all of that and return the behavior of your circuit. Um, any questions about this one?
Yes. So, what's the restriction on the type of device or component level models? Like, here I just see like the input is like just waveforms. So, do you just need to provide the S matrix and those
Um,
waveforms,
so
regardless of how you get them? Say like with analytical or experimental or simulation data. Is that how it works?
um, sorry, I'm not sure what you're asking. Are you asking about like the circuit model for the component?
I'm describing like what's the input, like what kind of device or component
Mhm.
models are allowed.
Yeah. So for a circuit, you don't really need to specify the model of the circuit because the circuit model is generated by IPKIS. But for the components inside of a circuit, you would need to specify um, the the compact model for that component. So you can specify it. The most common way is using like some sort of S matrix or like S parameter file. I'm sure there's other ways to define it. I mean, in Python, like just about anything is possible, but my understanding is that it's defined using like an S matrix. Does that answer your question?
Yeah.
Okay, great.
Makes sense.
Uh, Cool. All right, I'll go ahead and move on to the next file then. So now I'm just going to show you a frequency simulation for an MZI, and then IPKIS can do time domain simulations as well. So I'll go over that. But this is again, pretty similar to our previous setup. Import the things we need, um, visualize our MZI with a path difference of 100. Then we specify our wavelength range, specify here we're just making a list of path differences, starting from 50 to 150, spaced with 3 points in between. We have this for loop right here, and all this does is it iterates through each MZI, changes the path difference, and simulates the MZI at different path differences. So when I run this guy, what it's going to do is we have our visualization, um, and then we're going to, it's going to go ahead and run the first simulation. So here's our first simulation here. We can see it shows us transmission over the wavelength, gives us the FSR. Um, then we have our path difference of 100. We can see that. And then we have our path difference of 150. So this is just an example of frequency simulation using RMZI. Now we're going to be talking about time domain simulations. So again, we're importing all of the things that we need. Here we define a ramp function. Um, so this just returns a simple linear voltage ramping function that we can apply to our circuit. So we have the ramping function here, returns f step. Um, then we have our dt that we specify. Our voltage function is then the ramp function that we defined earlier. We specify all the things for it to create our driving voltage function. Um, and then we specify an optical source and a voltage drive. So these are just like some things inside of IPKIS that you need to specify for a time domain simulation. So we use yeah, function excitation. We say that the domain is optical domain, then we have our excitation function. Port domain, again, for the voltage drive electrical, and then our excitation function is the voltage function. And then lastly here, we're going to be making a test circuit, right? So we already have a circuit, like, yeah, like you can make a circuit for layout, but then this is a circuit for testing, right? For the time domain simulation. So we have i3.connect components, we specify our cells, we have a MZI, we have an optical source, we have a voltage source, and then we have our optical probe. And the links is basically the connections, right? So this is pretty similar to how you put a regular circuit together. We're specifying all of we're specifying how everything is connected together, and then we have a result here, which is we're going to get the time response. We're going to run get time response function on our circuit model of our circuit. We specify T0, T1, the DT, and then the center wavelength, and then we're just going to plot it. So when I run this guy here, it'll go ahead and first visualize the circuit for us, and then it'll go ahead and do the simulation. Right, here we go. So now we have our MZI thermal tuning in the time domain. So you can see that you can see the output power change as you change the voltage. So this is like pretty helpful, pretty useful for, when you need to do a time domain simulation on your circuit and see how it performs over time. Any any questions about this? All right. If no questions, then I'll go ahead and talk about the numerical link. Um, so the numerical link is kind of like it's like an it's a toolbox inside of IPKIS that helps you to run numerical simulations on your IPKIS components, right? So essentially the ideal workflow for it is, let's say you want to design a 1x2 MMI, right? You have a general idea of how the MMI is going to look. You have a general kind of starting point for it. You know that you need a 1x2 MMI for your circuit. So what you do is then you make the P cell first, right? So in here, we looked at the MMI P cell. So you go ahead and you make this P cell first. You say, okay, I'm going to make this P cell. It's going to have all of these things that we can change. It's going to look like this. It's going to have the ports here, so on and so forth. You make your P cell. Um, and once you make your P cell, then you say, okay, I'm going to take that and I'm going to import it into Lumerical and run let's say like we run an EME simulation on it, right? Um, so here we're making a very simple function, simulate splitter by Lumerical, takes in a layout, takes in your project folder, data tag, wavelength range, and then simulation gap. So here we're defining the simulation geometry, and we're using a ipkiss command right here, ipkiss.devicesim.simulation geometry. The layout is going to be the layout, and then we're modifying the bounding boxes a little bit. Then we define our simulation, right? We define the geometry here, we define the simulation here, and now we're going to say that we want a EME numerical simulation. We pass in our simulation geometry. We define all of our monitors. Um, and then we define the output. So the monitors here, we have ports, and then the output is going to be an S matrix over a specific wavelength range with a certain name. Setup macros, essentially, it's like if there's something else that you want to do with your simulation that IPKIS doesn't have commands for, you can basically just run these macros. Um, so, sorry, that's a bad explanation. Setup macros is just extra stuff that you want to set up with your simulation. So in this case here, right, we want to add group spans and cells to our EME setup. We want to add transverse meshes to our setup as well. And then for anything else that there isn't like a command for, you can just pass in numerical script commands. So in this case, we're setting all of our boundary conditions to be PML. And then project folder is just project folder, verbose, headless. These are just things for how it's going to run the simulation. Verbose just means it's going to print stuff in the console. Headless just means that it's not going to show the numerical simulation running when it runs. Simulation.inspect, it's just going to show us the numerical file before it runs. Simulation.get result, this just gets the S matrix from our simulation. And then we define the transmission and the reflection. We return it. And then in this code block here, we grab our 1x2 MMI from the PDK. In the layout, we specify our MMI parameters. And then we run this function and we retrieve the transmission and reflection, and then we print it. So I'm going to go ahead and run this, and it'll go ahead and do what it does best. And one thing I want to mention here is that, we didn't remake the geometry here, right? We already made the P cell and we passed the P cell into our numerical simulation. Um, Same with the, oh, that's great. Okay. Same with the ports here. We're not redefining the ports. Um, it takes the ports from the layout and then it attaches ports to them in your numerical simulation. All right, just give me 1 second. Um, Sometimes my numerical doesn't run if I don't manually start the license, so just let me do that real quick. Um, yeah, so it's like, you like the nice thing about this is that there's no translation error between your layout and your simulation, right? Because if you make your component in IPKIS, um, and you define where the ports are, you define what the simulation geometry looks like, and you port it to numerical. It's essentially a one-to-one port, right? You're not because you're not redefining the layout, you're not redefining the ports, you're not redefining everything. Everything is just being ported from IPKIS into numerical. Okay. All right. So now we'll wait for a second. Hopefully we are all good to go. Um, Here it is. Nice. So here it is. Here's our MMI, right? So, you can look in here. It has all of the layers for everything. Um, and all of these layers actually come from the PDK. So if you're using a Foundry PDK and you're developing a component for a specific process, you don't have to define the layers. It pulls it from the PDK and populates it for you and sets up your component correctly. And then here in EME, we can see all the cells for our EME simulation. You can see the ports, 1, 2, 3. And then if we zoom in here, we can see the port is literally right at where it needs to be, right? It's right at the MMI input. There's no gap, there's no weird spacing. It's right there. Then once you inspect your simulation, you take a look at it, you're like, all right, this is good. And even, if you look at the thickness of this MMI, I'm going to try to show you the thickness of it. Yeah, the thickness of this MMI is like, defined from the PDK. Everything is from the PDK. So you don't even have to worry about making, changing the thickness or defining that. Everything's from the PDK. But once you go ahead and, inspect it, looks good, go ahead and close this guy, and then it'll start running it in the background and it'll print stuff to the console. And while that's running, I'm going to go ahead and just talk about optimization as well. Because this is essentially just a simulation recipe for this component, right? Um, and so, it's like you basically um, like you write the recipe once, right? And then you can modify the recipe as you need to simulate your MMI. So let's say, like you define this MM or you design this MMI and it's perfect and it works super great for your layout. But you finish your PhD and you move on to, the next step. The person that comes in and continues the research or continues or takes over this MMI, they no longer have to rewrite the simulation routine or rewrite the code, right? Because it's already all written in IPKIS. It's already all inside of a central, ideally inside of a like a repository, right? Um, the person can come in and say, okay, I already know how to simulate this MMI. I want to simulate this at, 1310 instead of 1550. Let me just change this, do the simulation. Okay, cool, great. That works. That looks good. Now let me go ahead and optimize this MMI, at 1310. And, you know, now you have an optimization routine that the person can write for 1310. And even then they can take the optimization routine for 1550 copy it, change it up a little bit so that it optimizes at 1310. Um, so that's like the big advantage here is that you write the code once and you can reuse it as many times, reconfigure it as many times, and it's the code is like it's easy to pass it down because otherwise from my previous experience there's always simulation scripts like floating around on different computers. One person has it, another one person has one version, another person has a different version. Nobody knows what the latest version is. So if you put everything in ipkiss, you code it in Python and you use GitHub to manage everything, then it ensures that everyone has the latest version of your simulation and layout scripts. Um, but here in the console, it tells us now it's printed the transmission and the reflection for our MMI. So once it does that, now we want to optimize our 1x2 MMI. So here again, we import the things we want to use. We import our PDK, optimization file, optimize MMI, define our trace template, and then this is a function here that we are accessing. So this is an optimization function. It uses the minimize utility from SciPy. We have all the things that we want to take in. And then we have our cost function here. And then the result is the minimization of the thing we want to minimize plus all these other things. And then we plot the result of our MMI. And then we also print the optimization. So I'm going to go ahead and run this. And what this will do is this will optimize our 1x2 MMI at 1550. So one thing I want to note with this is that this is not using Lumerical to optimize. Or sorry, it's not using Lumerical for simulation. It's actually using Camphor. Camphor is a built-in EME simulator that comes with ipkiss. And it's usable. If you want to use it, you totally can. But I personally trust the results of Lumerical more. Um, so we're just using Camphor in this demo because Lumerical could take some time to generate all of these results. But as you can see here, right, it's changing the length, changing the waveguide spacing, changing the taper width, and it's reporting the transmission of the MMI based on the parameters that it changes. So
Hold on. What what's it optimizing? Like what's going on under the hood?
yeah, so what this is doing is it takes the MMI P cell that we have, right? And then it changes the geometric parameters of it, and it runs an EME simulation. Um, and it uses a minimize function to basically like maximize the transmission while I guess minimizing the and basically to maximize the transmission of our MMI. So under the hood, it's just like going through every possible permutation of the MMI based on a specific range, runs the EME simulation, gets the transmission for it, and then picks the one that has the best transmission at a certain wavelength.
Oh, okay, I see. So there's some optimization algorithm
Yes.
going on.
Yep. Yep.
Not
Exactly.
not just what do you call it? Not just a parameter sweep.
Yeah. No, exactly. Exactly. It's not just a parameter sweep. It's optimizing using SciPy. And yeah, we also have links to Tidy 3D. But yeah, the main idea with this is like, it's like you define the simulation recipe once, you define the optimization routine once, and then you can, change it up, reuse it as many times as you want. Same with the layout, right? You define a splitter tree layout once, and then you can have as many different permutations of that splitter tree as you want. And then especially if you manage it with GitHub, then everything is like all centralized, and it ensures that everyone has access to the latest version of the code. Then while this runs, there's another thing I want to show you guys. So this will take a little bit. This should end soon, but any questions so far about anything we've talked about? I know I covered a lot in this session, so do you guys have access to trial licenses? Have you been able to try it?
I got the license. I haven't gone around to try it yet. I will shortly.
Gotcha. Okay. Yeah, no worries. No worries at all.
I'm in the
Hopefully
same
this is
situation.
gotcha. Yeah, no worries. Hopefully this has been kind of helpful in showing you what IPKIS is capable of. Um, and hopefully you guys are able to kind of think about how you can apply this to your research and to your projects. All right. While this guy's running, maybe I wonder if I can run two things at the same time in Python. Let me try. Okay. All right. Cool. Nice. We've got this guy running in one tab, another one running in the other tab. Okay. So very quickly, I just wanted to show this generalized splitter tree file. And um, basically, right, this is a splitter tree we were looking at earlier, but now we have number of levels as a parameter, so we can change the number of levels in here. So, you know, we've really stepped through, right? We started with a very simple splitter tree to a splitter tree that we can add to different circuits and change the splitter and couplers for, to now we have a splitter tree that you can change the number of levels for, right? So right now when I ran this, it's going to return a 4-level splitter tree, 1, 2, 3, 4. But if I close this guy and run let's say a 7-level splitter tree, it will generate a 7-level splitter tree for us. And here we go. Here's our big splitter tree. So, yeah. Um, that's you can take your layout as far as you want. You can do as much as you want to it. So there's a lot of reusability and reconfigurability of your code, and especially with the power of Python, right? You can automate a lot of stuff. You don't have to hard code many things. You can have stuff tied to the input parameters. So yeah. All right, we have 3 minutes. Okay. So it's printed our optimized MMI. So this is the MMI that it thinks is the best. And then now it's going to tell us what the parameters are for that MMI. Oh, here's the EME profile for it. And then now it tells us that the optimal length is 14.19 microns. The optimal waveguide spacing is 2. Optimal taper width is 1.5. Optimal width or it didn't actually change the width or the taper length. So then it tells us that the width is 4 and the taper length is 5. And then this right here is our result. So this is the best transmission it got. And yeah. Um, what else can I show you guys? what's in here? So this is a splitter chip. It's a little different from a splitter tree. So essentially what this is going to do is, so earlier I talked about, importing your layout into another layout, right? So you have your splitter tree that we made earlier, and we're importing it into this layout and adding all of our IO to it, right? Um, so we have a waveguide crossing that we have in here. Um, we have, what else do we have in here? So we're using a couple new different things. We're using align V and align H. This basically just aligns. So we're aligning the waveguide crossing in either the vertical or the horizontal axis relative to the grading coupler or the tree. We have the place command, placing our tree, connect Manhattan, control points. So this control point here is controlling the route that we're making. So this is controlling the route between one of the crossing inputs to the test grading coupler. So that would be this route right here, right? So IPKIS doesn't really know where everything is. So I know we're like at time, so I'll do this very quickly. So basically, instead of IPKIS will automatically just route it at the shortest path. Boom, 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 which goes to the tree. So we're saying here in this control point, we're going to take the horizontal movement of the route, and we're going to first bring it down to the south side of the tree, and then we're going to bring it down to half the Y spacing, and then continue with the route. So that's what's going on in this line right here. Another thing is connect Manhattan bundle, which just connects all the waveguides in a bundle. And yeah, that's pretty much it. Any like last minute questions? Because if not, then I'll just go ahead and end the session right here. All right. Cool. Thank you guys so much for coming. I hope that this was helpful, and yeah, I hope that the IPCIS trial goes well for you guys, and yeah, let me know if you have any questions.
Well, thank you so much. Thank you so much for taking some time out of your day to do this. And yeah, thank you.
Yep, no problem. All right.
Thanks.
We
Yeah, of
appreciate it.
course, no problem. No problem. All right. See you guys later. Thank you.
Thank you.